Hey guys, welcome back to Pop 'em Up Chem. We're carrying on with Unit 10, Organic Chemistry, and in this video we're going to be looking at isomers, which we alluded to in the first lesson, how we could arrange compounds differently. So let's see what we're going to get up to. So, as usual, there's a little refresh question from last video, which is listing 3 characteristics of homologous series. So before you get on with that though, let's just have a look at what we're going to try and do. So the first thing we're going to look at is the 3 types of structural isomers. Hopefully that will give us the skills we need to be able to draw and name non-cyclic alkanes and alkenes, and then develop with the IUPAC nomenclature system. For those not in the know, IUPAC is the International Union of Pure and Applied Chemistry. Basically, it's an organization that helps set standards that allow information to be shared within the scientific community more easily and more uniformly. If you haven't already, pause the video, answer the question from the last lesson. Okay, so hopefully you got that there are the general formula, which is usually taken the format of the example here I'm giving of alkanes, the chemical properties such as the reactivity or the reaction with alcohols per se, and the functional group, so that's the part of the molecule that is indeed reactive. In this video we are going to address isomerism. So isomerism falls into 2 large parts. We've got stereoisomerism, which we'll look at in HL only, that's geometrical and optical, and then we have structural, which can be broken down into 3 parts: chain, position, and functional group isomerism. And an isomer is a compound with the same molecular formula but a different structural formula. So that's all of the same atoms, the same number of atoms, but they are arranged in a different way. And there are 5, as are shown here, different ways that we can arrange these. So here are some isomers from C4H8O. Now these are all structural isomers. You can see they all have 4 carbons, as this one does here, and we can see that if I just quickly show where all of the hydrogens would go on this formula, you can see, including on the OH, we have the correct number of hydrogens there. And even coming down to this epoxy at the bottom, we can see we've got 4 carbons, and also if I fill in where all of the hydrogens would be, we also have the correct number of hydrogens down here. And in all of the isomers that are on the board here, we're not including any of the stereoisomers, the geometrical and optical isomers that we're reserving for HL. These are all the structural isomers. But we want to break these down into further categories. And so there's 3 types, as we've mentioned before. There's position. So if we give an example here, let's draw out a nice simple compound. So we're going to draw out bromopropane. And we can see that the bromine group is on this last carbon. Okay, and we know from what we did last lesson that is a primary. But we could put the bromine on this central carbon and make it secondary. And this is what we would call a positional isomer, because now we have the secondary isomer. That's different from functional group isomerism. Functional group, we have all the same things here. So here I've got an aldehyde, I've got propanal. And if I move the C double bond O group, if you like, into the middle central carbon, we create the ketone, propanone. So what we know from functional groups from last lesson, we know that this kind of isomerism is going to give vastly different properties to the compounds because they have different functional groups. Chain isomerism occurs when we have a chain that is long enough for us to shift the length of the longest chain or shift side groups to make alternate pathways, if you like. You can see here, all we're really doing is taking this methyl group and putting it on one of the central carbons. So here I've just kind of put a summary definition for each of the 3 that you can get down, just so you can also see in words what each of these things pertains to. So a quick note on drawing straight chain isomers, and a common mistake that students often make when they're first drawing these. Let's draw out a couple here. So I'm going to draw out a chain with a methyl group here, and I'm going to just draw the rest of it as a saturated molecule. So we've got what looks like a 3-carbon chain with a methyl group, or at least that's how it may appear initially. Now in this situation, I'm going to draw a very similar thing, but I'm going to change the position of where the CH3 group is. Now it may be more obvious that the one on the right is actually a 4-carbon chain length than the one on the left. However, we can rotate around bonds. When we've only got single bonds, so again, going back to your unit 4, when we've only got single bonds, we know that we have hybridized bonds that are interatomic axis. They are parallel with that, and so they can rotate around it. And that means that that CH3 group could be on any position of that final carbon. So it can sometimes be confusing, at least initially, to determine where your chain is. So make sure you're always just counting the longest chain length, reiterating what we did in the last lesson, so that you know that these two represent the same thing. So let's get started with this. What I want you to do is I want you to have a go at drawing the non-cyclic alkanes. So I want you to draw full structural formulas for every isomer of the alkanes with n equals 6. That's C up to 6. I want you to give yourself space in your notes around these, because we're going to use these molecules and we're going to name them and do further things with them. A little tip is there is 13 of these in total. I want you to pause the video and I really want you to have a go at this. Don't worry if you get things wrong. Remember what I said last lesson. You really doesn't matter if you're getting things wrong initially. There are 13 you're looking for. And bearing in mind what I just said about the position of a methyl group at the end of the chain contributes towards the number of the parent chain, I want you to have a go and draw all of the isomers up to n equals 6. Okay, how many did you get? As I said, there was 13 in total. The first 3, there are no isomers, okay, because we can't move any of those methyl groups. But if we take straight chain butane and we move that methyl group into the center, then we end up with our 5th one here. We can do the same with our straight chain heptane. We can form the 7th one, and we can also take a further methyl group and place it onto that same carbon to make the tertiary isomer there, number 8. And you can think of this process, you can see, I'm just going to keep drawing it out. You can think of this process as we're just moving the methyl groups along and seeing if we get something novel, seeing if we get something new. So once we get up to hexane, we can actually have that one methyl group in 2 different positions. And then we can also take that methyl group and pop it onto one of the central atoms, and we can have 2 variants of that. One where the methyl groups are on different centralized carbon chain atoms, and one where they are on the same, giving us 13. And if you did the extension, here are all of the molecules in their skeletal formula. You can see what I like using this because I'm lazy and it just looks nicer on a page. But if you're not used to it and you don't want to use it, that's completely fine. But you may see me use it from time to time. So now we can draw these. Let's name them. So we're going to use the suffix ane, and we're going to use the prefix from the longest carbon chain. So here's an example. I have 2 carbons as my longest carbon chain, so I need to always identify the parent chain length. And so that means it's going to be eth and then ane, ethane. Okay, let's have a look at another example. So here I have a straight 4 carbon chain. Now if I have 4 carbons that go across the middle, 1, 2, 3, 4, then it is going to be bute, so it's going to be butane. So when we look at branch chain alkanes, there's more things we have to consider. So I've kind of set up flow of the way you can sort this out. You don't have to go in this order, but it can be helpful, especially when you're beginning. So let's start with a branch chain alkane here. So we can see already we've got that methyl group up top. So we want to find the longest chain, just like we did before. Now, if we go across and up, then we find we have 3 chain. And if we go right to left and up, we find 3, and we find 3 across the middle. So the longest chain is definitely 3, even if we use the middle one. Now, what I'm going to do is I'm just going to use the middle 3 just because it's easiest to visualize, but it wouldn't matter what you did this if you follow these rules. So we want to now identify the size of the branch and the position of the branch. So that's the piece that's coming off. So you can see up here, the branch has 1 carbon. 1 carbon, if you look at the branch size section here, is going to be a methyl. And also we want to donate the position. And so we're going to number the carbons along that centralized chain. And then we're going to say that it is attached to the second carbon. Now we're going to choose the numbers when we number that middle chain that would cause the lowest number. That's not really relevant for this one. But if the branch was closer to one end than the other, we would always choose to number our parent chain carbons from the end that is closest to those groups to reduce the number that we're going to put before it. But what does that mean? Well, that means we're going to have 2 methyl is going to be the thing that's going to come before. Because we're saying 2 is the carbon the methyl group is attached to, and methyl is the size of the branch. And once we've done that, we simply add the name based on the parent chain, which in this case is propane. So we end up with 2-methyl propane. So let's do another example to try and work through that process again. So in this molecule, I'm going to draw a slightly larger branch because sometimes that can throw us off, and we need to make sure that we're counting our longest chain, our parent chain, very effectively. So we're trying to find the longest chain. So let's have a look here. 1, 2, 3, 4, 1, 2, 3, 4. But if I go from here, 1, 2, 3, 4, 5, 6. Okay, so my parent chain actually runs from here to here. So I actually have a 6 parent chain. So I have a hexane parent chain. And then I have here a methyl group. And remember, I want to determine the number of the carbons. So I'm going to label the carbon chain going in one direction and in the other. And remember, we always want the number that gives us the lowest number. So that in this case is the number I labeled in green, which gives us the number of 3. So this will be a 3-methyl. Remember, we're minimizing the numbers. So we've got 3-methyl and we have a 6 carbon chain in total. So we have 3-methyl hexane. Okay, let's do another example, but this time let's get some multiple branching going. So I'm going to draw a kind of just straight, simple backbone here. And then I'm going to put a CH3 here and one on this carbon as well. So we're going to go through the same process again. Remember, count the longest chain. In this case, it doesn't actually matter if I choose to go up or down. The longest chain here is 5. So I'm going to have a pentane at the end of the day. I'm just going to choose this straight middle line just because it's the easiest to visualize. Then we want to identify here, we've got a methyl group and another methyl group. So it's going to be dimethyl. And then we want to count our parent chain. So I'm going to count 1, 2, 3, 4, 5 in this direction. Now, if we do it in the other direction, 1, 2, 3, 4, 5, you can see that we're going to have larger numbers if we use the red numbers. So I'm going to pick the other numbers and label from right to left. So this is going to be a methyl group on the 2, then a methyl group on the 3, di to indicate that there's 2 methyl, and it's pentane because its parent chain is 5 carbon long. So going back to the isomers of alkanes below n equals 6 that you drew earlier, you're going to have a go at naming all 13 of those. Pause the video, have a go at using the skills we've developed so far to name all of these then. Okay, so let's have a little look at the answers. So the first few should be pretty easy using your suffixes. We've got methane, ethane, propane, butane. All we have to do for number 5 is we've got a 3-carbon chain. So we've got 2-methyl propane. Then we've got pentane. And then we take one of those methyl groups, move it along, number our parent chain, and we get 2-methyl butane. Going on to the ones we have left over, moving another methyl group on that, we end up with 2,2-dimethyl propane for number 8. Number 9, we just have 6, so it's just a regular hexane. Moving a methyl group, labeling from the right to left, we get 2-methyl pentane. And then we can move that methyl group along. Doesn't matter how we number the chain on this one, we get 3-methyl pentane either way. If we took that molecule and then put a methyl group not on the same carbon, wouldn't matter how we label the parent chain, we get 2,3-dimethyl butane for number 12. And if we put them both on the same carbon and label the parent chain, we get 2,2-dimethyl butane. Okay, so with alkenes, they have a very similar process and very methodical naming process, just like the alkanes. The difference is hopefully you know by now that this includes a double bond. So we've got the example of ethane and propane here. So you're going to, once again, draw full structural formulas just for the straight chain alkenes. So you don't need to do the branched alkenes up to C equals 6, and the isomers will come from where in that chain the double bond is. Just to give you a clue, there are 9 in total. So go ahead and pause the video and try that. Okay, so did you get all 9? I've drawn them skeletally here, but you will have drawn them like this, where you have a double bond and then you have your hydrogens around. Now, again, the first couple do not have isomers because it doesn't matter where we put the double bond, it ends up looking the same. Once we get to butane, however, the story looks kind of different, right? Because we can put the double bond on the edge, like the first one I drew, or we can put the double bond in the middle. And this is how alkenes form isomers. So on the top right, we would call this but1-ene because the double bond is in between is on the first carbon, and the bottom left we have but2-ene. So the number in the hyphen lets us know where in the molecule, in the parent chain, the double bond is. So we can go through these C up to N equals 6 and name them. We've got ethane, propane, we've got but1-ene, we've got but2-ene, the ones we already described. Then we get pent1-ene for the 5-carbon, pent2-ene. Notice we don't get pent3-ene because if we move the double bond there, we just count the parent chain from the other side, and that just becomes pent2-ene, but looked at from the other angle, really. Then we get hex1-ene, we get hex2-ene, and because hexene is long enough, it also has the hex3-ene. So we've been building a system here, or at least something that feels like one, and we're getting towards one. And that is where we want to bring these ideas together, these preliminary ideas together into the IUPAC rules for alkane nomenclature. So we've actually done a few of these steps already, and many of them will look familiar, like finding the longest continuous chain, identifying groups attached to the chain, numbering consecutive carbons, and designating locations. We've even had a little look at prefixes. One thing I haven't mentioned yet was my use of commas between numbers and dashes between numbers and letters. when you're using, 2-methyl propane. Now, you probably won't lose marks for this, but these are the technical rules. So this looks like what we've already done, but now we want to broaden it out to all the functional groups that you spent so much time researching in the last video. So let's look at an example. Why don't I start us off with something like a branch-chained alcohol. So again, we're going to do all of the things we've done before. We're going to find our longest chain, in this case 3, and we're going to find any substituent groups. Once again, it doesn't matter where you pick this from, you're going to find an alcohol and you're going to find a methyl group that is going to be on the second carbon. You could have also done the L-shaped chain, so we can number the chain 1, 2, 3 or 1, 2, 3. Now, again, we want to keep the alcohol number as low as possible. So we're going to do 2-methyl propan 1-ol. And in that way, it's very similar naming alcohols as the alkenes. Let's try another one though. So this time, let's add some halogens into the mix, and maybe also a chain as well that we have to deal with. Let's just go through the processes. Again, finding the longest chain, we've got a parent chain of 5. I've got a dichloro to deal with, and I've got a methyl to deal with. Now I want to make sure I position these correctly. So remember, you can number the chain from both sides and check which one's going to give you the overall lowest number. So we're going to get here 1,1-dichloro dash 3-methyl pentane. So a toughie, but I think you can all do it. And time to have a go. Name this compound then. Pause the video. Pop 'em up! Hopefully you got propan 1-ol, 3-parent chain, alcohol is on the first carbon. Nice and simple then. Try your hand at this one. Pause the video. Pop 'em up! So we've got a butan 1-ol, so I know I'm going to have that 4-carbon backbone with the alcohol on the first carbon, and it says 2-chloro, so the chloro will be on the second carbon, and I'm just going to fill in my hydrogens from there. Simple as that. 1, 2, 3, 4. Lovely. Okay guys, so there will be an accompanying video on modeling molecules using Molymods, and that will help you answer questions that will be in the practical workbook on the construction of 3D models. I will notify you when that has been uploaded. In the meantime, you really should be spending time practicing because it's handy if this feels natural. Thanks for joining me on another episode, guys. Like, subscribe, and as always, practice makes slightly better.